All right, everyone, this is section 2.7, polynomial and rational inequalities. So when we solve a polynomial inequality, we're going to follow a few steps. We're going to start by making sure our inequality is set less than or equal to 0. And we're going to solve the related equation. Those solutions are going to represent the boundary points of our solution intervals. Those solutions are going to go onto a number line, setting up our intervals. And then we are going to test specific values on each interval. I'll talk about this idea of using signs to save time in just a moment. And then finally, we are going to write our solution in interval notation. So let's take a look. Here on example 1, I have x squared minus x is less than 20. So I'm going to start here by moving that 20 over so that my inequality is related to 0. Now I have a quadratic. I'm going to solve this through factoring. I'm going to factor this to x minus 5 times x plus 4. So the key critical values that are of interest are going to be 5 and negative 4. We're going to put those values on a number line, like you see here. And basically we have 3 intervals to check. We need to test the interval from negative infinity to negative 4. We need to test the interval from negative 4 to 5. And we need to test the interval from 5 to infinity. We can plug in specific values, but what I like to do is I like to use factored form. If I were to plug in, say, let's fill this out. We're going to test negative 10, 0, and positive 10. Any number on these intervals will do. I strongly suggest you choose values that are easier to work with. If I were to use factored form, if I were to plug in negative 10 here, negative 10 minus negative 5 would be a negative value. And if I were to plug in negative 10 to my second factor, negative 10 plus 4 is also negative. I'm trying to see if this quantity is less than 0. What I see here is that that is not true. I would have a positive number, right? Because I have a negative number times a negative number. If we were to actually plug in negative 10, we'd get 90, but in either case, this particular interval does not achieve a true statement. If I were to plug in 0, I would get a negative number times a positive number, which we know is negative. We're saying, is that less than 0? It is. So this interval does work. And then finally, for our third interval, we're going to test again. If I were to plug in 10, I would get 10 minus 5, which is positive, and 10 plus 4, which is also positive. I can see that that quantity, a positive times a positive, is not negative. So this part of my inequality would not be part of my solution set. I really think that using the signs here, right, and as long as we're in factored form, using these signs can really speed up this testing process. So our final answer here is going to be on the interval negative 4 to 5. The original problem was an inequality and not equal to. So our interval would exclude the endpoints, but our solution set would be all values from negative 4 to positive 5, excluding the endpoints. Let's look at a little bit more complicated one. Here we have a cubic, x to the third plus x squared is less than or equal to 4x plus 4. I'm going to start by setting this inequality set as less than or equal to 0. I have 4 terms. I'm going to factor this by grouping. And I can continue factoring here. X plus 1 times x squared minus 4, or x minus 2 times x plus 2. So I can see that the key values on my number line are going to occur at negative 2, negative 1, and positive 2. I can see here my 4 intervals that I'll need to test. on my number line. And I know it may seem excessive to include this number line, but I really do think it's easy as a visualization tool. So this number line tells me where I'm going to test. I'm going to test from negative infinity to negative 2, from negative 2 to negative 1, from negative 1 to positive 2, and from 2 to infinity. And you can see here, if we're going to use 4 intervals, it's going to help us if we can speed our pace up. Our test values here, we can use whatever we like. Negative 10, negative 1.5, 0, and 10 are what I chose. Nothing necessarily special about these, just ones that I felt were the easiest to deal with. So I'm testing to see, do these quantities, are they less than or equal to 0? So we can plug in, right, a large negative value. And I'd be left with a negative times a negative times a negative. 3 negatives does in fact lead us to a true statement here. So this would be part of my solution. My next test is going to give me a negative value, and a positive value. Right, one of my factors would be positive, so therefore this set would not be part of my solution. My next set, if I plugged in 0, I'd get a positive times a negative times a positive, with a single negative value that is part of my solution set. And then finally, if I were to plug in positive 10, all quantities, all factors in factored form would be positive. There's no way that could be a negative number. So this would not be included in my solution set. So when I write my solution set, I also want to pay attention to the inequality symbol that I used here, the less than or equal to. So I'm going to include negative infinity to negative 2. And because we had that less than or equal to, I'm going to use that square bracket in union with negative 1 to positive 2. And I apologize, that first bracket should be square, as should the last one. So there's our solution set to this inequality. Again, we solve the related equation, use those solutions as parts, interval setups for our testing, and then we test each of those intervals and find the ones that get us a true inequality. If we want to visualize this, we can see that on our number line, the areas that did work were our first and our third intervals, and our second and fourth were not successful. We can move on to solving rational inequalities. We're going to treat these very similar. However, we also need to account for vertical asymptotes. Okay, so when we find those critical values, the values we're going to put on our number line, we want to find not only our zeros, but also vertical asymptotes. We're going to test points on either side of any zeros or asymptotes. And when we get to the end to give our final solution, we will exclude the endpoints of any that involve vertical asymptotes, because even if we have a less than or equal to or a greater than or equal to statement, those values would make our denominator 0. Let's look at a few examples. So here on example 3, I want to set this inequality equal to 0. So I'm going to have x plus 1 over x plus 3 minus 2. And I'd rather have this as a single fraction, so I'm going to find a common denominator, and I'm going to let that be x plus 3. You can see here that I've multiplied negative 2 times x plus 3. And when I simplify all this down, I will get negative x minus 5 all over x plus 3. So the critical values on my number line will be negative 5, the value that would make my numerator 0, -3, that would make my denominator 0. So this is a 0, and this is a vertical asymptote. So again, I'm going to create 1, 2, 3 intervals that I can now check. So the first interval I'm going to check are going to go from -infinity to -5. My second interval will go -5 to -3. And finally, my third from -3 to infinity. I can test any point I like. I like using multiples of 10. They seem just a little bit more friendly for me. For my second, I'm going to pick -4. And finally, for my third, I will pick 0. Again, I like to use this idea of just using signs rather than worrying too much about the specific values. If I were to plug in -10, I would get a positive number divided by a negative number. My original inequality was testing, was it greater than or equal to 0? And I can see that with a positive divided by a negative, that is not true. If I were to plug in -4 into my simplified form, I would have +4 minus 1. So I would have a negative value divided by a negative value. Is that greater than or equal to 0? Well, it is in fact, because a negative divided by a negative would get me a positive. If I were to plug in 0, I would have -5 divided by a positive value in my denominator. I'm evaluating, is that greater than or equal to 0? And in this case, it is not. So through the same process, I am using symbols to make sense of what's going on. The only interval that works for this particular problem is my second interval, but I have to be careful. I need to know what exactly each of these points represent. -5 is an x-intercept, so I can include -5 in my solution set. However, -3 is a vertical asymptote, so even though we have a greater than or equal to symbol, I would exclude -3 from my solution set. I would like for you guys to try example 4 on your own. My recommendation here is that you subtract this inequality, the fraction on example 4 over to the other side. Do not multiply. Get a common denominator and simplify from there. All right, let's see how it went. So you can see my algebra work here on the left. I have moved all my terms over to the left-hand side of the inequality so that we are all less than or equal to 0. I just want to reiterate, we don't want to multiply both sides of this equation. We are going to eliminate intervals. We're going to eliminate asymptotes, and that's going to cause us a headache. So what we want to do is we want to create a single equation on the left-hand side of our inequality. A single fraction on the left-hand side of our inequality, and then simplify that as best we can. We want to keep it in factored form so that the intervals that we test will make sense. Well, when it's all said and done, I was left with this inequality here, -x plus 10 over x minus 3 times 2x plus 1. That leaves me with 4 intervals, and what I have on my number line here, I've highlighted these two values at -1/2 and +3 because they are vertical asymptotes. They are coming from our denominator. So I know that I'm going to have to treat those differently once I get to the end of this problem. So those 4 intervals are set up as you see here. I use these specific values, -10, 0, 5, and 20 for these intervals. But when I evaluate, I really do just focus on the signs, right? I focus on, will my numerator become positive if I plug in -10 or negative? And then I can kind of use what I know, right? A positive divided by a negative divided by times a negative would result in a positive. It is not less than or equal to 0. So that's how I determine that this specific point fails the test. I work my way through, and I find that the second and fourth intervals are both legitimate. Again, I need to pay attention to what those endpoints represent. That's why I highlighted those on our number line. -0.5 and 3 are both vertical asymptotes, so I want to exclude those from my solution set. Last thing we have in our notes here is a projectile motion application problem. They give us a function. They tell us that the object in free fall can be modeled using this function. And they tell us what that v0, that initial velocity, and that s sub 0, the initial height, is. So in this particular problem, we are throwing a ball vertically upward from the top of the Leaning Tower of Pisa, which is 190 feet high. So our function will be -16t squared. Our initial velocity is 96 feet, so that'll be plus 96t plus 190. Now they are asking us during which time period will the ball's height exceed that of the tower. So this function that we have on the page is the height of the ball. We want to know when this function is greater than or equal to the height of the tower. Well, we want to set this equation equal to 0, so we'll be left with -16t squared plus 96t is greater than or equal to 0. Well, this is now just turned into an inequality, a quadratic inequality, so we can factor out a -16t, and we'll be left with t minus 6 is greater than or equal to 0. So our number line, our setup, will include values of 0 and 6. Our three intervals are going to go from -infinity to 0, 0 to 6, and 6 to infinity. In the context of the problem, I think that this first interval has very little meaning, right? If our input is time, negative time isn't really useful for our function. So all we really need to do is test two intervals. Between 0 and 6, let's say we'll check let t equal 3. And then between 6 and infinite, let's let t equal 10. Well, if I were to plug those values in, I would get a negative number times a negative number. And I want that quantity to be greater than or equal to 0. And in this case, that is true. When t equals 10, I will get a negative number times a positive number. I'm testing to see is that quantity greater than or equal to 0, and it is not. So during what time will the ball's height exceed that of the tower? It will occur from t equals 0 to t equals 6, or in interval notation, from 0 to 6. And we are done.